Section 5.6 deals with how the intermolecular forces between molecules affects physical properties of a liquid. Intermolecular forces are the forces between molecules. Recall that London dispersion forces occur within all molecules. They are the primary force that holds nonpolar molecules together, and they are the weakest of the three. Dipole-dipole forces occur between polar molecules. They have very strong forces of attraction. And then there's the hydrogen bonding, which has the strongest forms of attraction, and they only occur in polar molecules that have a hydrogen, fluorine, oxygen, and nitrogen. The number and strength of intermolecular forces will affect the properties of a substance. Recall from several sections earlier, we have talked about how energy is needed to break the intermolecular forces so that molecules can separate. Well, energy is released when new intermolecular forces are formed. Intermolecular forces are broken during the phase changes of melting, where we go from a solid to a liquid, and evaporation, boiling, where we're going from a liquid to a gas. The stronger the intermolecular forces, the more energy will be required to melt and or evaporate and boil a liquid. Thus, the melting points and the boiling points will be higher. Recall that water is made up of oxygen and two hydrogens in a bent shape, and that it is polar because the dipoles are not canceling each other out. You need to know that water is also a very small molecule, and in general, small molecules usually have low melting and boiling points. So based on its size, water should be a gas under normal conditions. But it's not, it's a liquid at room temperature. And that's because of the polarity of water and the dipole-dipole attractions and hydrogen bonding that exists between the molecules. Because of the intense hydrogen bonding that holds the molecules together, its boiling point is going to be much higher than normal. And this is really important because we need water to exist in liquid form. Let's take a look at the boiling point of polar molecules. If we looked at the trend in green for H2S, H2SE, and H2TE, we would see that these are all polar molecules and they are getting larger in size. That means that there are more electrons moving around so that the London dispersion forces in these molecules is also getting greater. Thus, the boiling point is getting greater. But if we take a look at water, which follows that same pattern, you will see that it is an anomaly. It is at 100 degrees Celsius. Instead of being down below, where it would typically be, it's up at the top, and that's due to the hydrogen bonding that occurs within that polar molecule. The H2S, H2SE, and H2TE do not have hydrogen bonding, just simply dipole-dipole forces and those underlying London dispersion forces. And you'll see that pattern in the blue trend line and also in the red trend line. HF and NH3 have hydrogen bonding, and that makes their boiling points a lot higher than their counterparts. You can see that with the blue and the red line, every time the molar mass increases, the boiling point is increasing as well. Viscosity is a property, a physical property of a liquid, and it's the resistance to flow. Let me give you an example. Molasses, or syrup is much more viscous than water. One of the reasons why that is the case is because it has a stronger set of intermolecular forces. Why is that? Well, larger molecules have more London dispersion forces in them, and more forces generally means stronger forces. And so because these molecules are very large and they're very long and they get kind of tangled up, they tend to stick together more. So when more molecules stick together, we have a higher viscosity. One of the ways that we can reduce that viscosity is by increasing the temperature of that liquid. When we do that, it helps break some of the intermolecular forces and makes the substance less viscous and more easy to flow. Which liquid is more viscous, molasses or water? Hopefully you can see that the molasses is going to be more viscous. It's going to take a longer time to flow out of the beaker than the water. Solubility is the ability to have a solute dissolve into the solvent. Remember that the solute gets dissolved and the solvent does the dissolving. The universal solvent is water, but any liquid can act as a solvent. In the bottom example, you can see sugar is acting as the solute, dissolving into water, the solvent, and you end up getting a solution. Remember that a solution is a homogeneous mixture. It is a physical change. All the sugar molecules are evenly blending through the water molecules. Why does sugar dissolve in water? Let's take a look at the molecule of water and recall that it is polar, meaning that it has charged ends. It has a partially negative and positive end. Sugar is also polar. It has a partially positive and negative end. Because of the like partial charges, the opposite charges will attract, and the water molecules will take away the sugar molecules. As this process occurs and the sugar dissolves in the water, new intermolecular forces will be formed, releasing energy as the solvent carries off the solute. This is the process of dissolving. It is also called solvation. Here's another example of solvation. This time, an ionic compound is being dissolved by water. Recall that water has those charged partial positive and partial negative ends, and this time they will attract to the full positive and negative ends of an ionic compound's formula unit. You can see that the partial negative end of oxygen is attracting to the positive end of sodium, and the partial positive ends of hydrogen are attracting to the negative end of chlorine. If the energy needed to break the old intermolecular forces is much greater than the energy released when the new ones are formed, solvation will not occur. We say that the substance is insoluble. We have a rule of thumb called like dissolves like that will help us predict whether substances can dissolve or not in other substances. Like dissolved like pretty much says that polar solvents can dissolve polar solutes. Polar solvents can also dissolve ionic compounds because of the charged ends of both the molecules. Nonpolar solvents can dissolve nonpolar molecules. However, polar solvents cannot dissolve nonpolar solutes and vice versa. That is why oil and water do not mix. Water is polar and can hydrogen bond. Oil is nonpolar and it only has London dispersion forces holding it together. It's going to take a lot of energy to break the hydrogen bonds between the water molecule. Since water can only form London dispersion forces with the oil, that will not release a lot of energy. And because there is such a huge difference in the amount of energy needed to break and the amount of energy needed to form, we will find that water and oil are immiscible on one another. They cannot dissolve. Surface tension is the resistance of a liquid to spread out due to the uneven attraction of the liquid molecules pulling towards the center of the liquid. You can see an example of surface tension when you look at a freshly waxed car and water droplets form on top of it. The higher the intermolecular forces, the higher the surface tension. So water forms beads due to its high surface tension, giving it that perfectly spherical droplet. You can see that picture on the right. And because of surface tension, very light objects can actually float on water, as seen in the diagram on the left with the paperclip. Vapor pressure is the pressure of vapor molecules that are formed above a liquid. We've determined that the higher the intermolecular forces, the lower the vapor pressure. Only two factors affect vapor pressure. The first is temperature. As you can see in the diagram, as we increase temperature, we increase the vapor pressure of a liquid. Recall that temperature is kinetic energy that is being put into a substance, breaking the intermolecular forces. More molecules above a liquid in vapor form will have more collisions and thus make a greater vapor pressure. The other factor that can affect vapor pressure are the intermolecular forces, the attractive forces between the molecules. Taking a look at this diagram, you can see that there are three substances: diethyl ether, ethyl alcohol, and water. If we look at the boiling point of each of the three liquids, you will see that water has the highest boiling point at 100 degrees Celsius. And that's because it has the strongest forces. Remember, there is hydrogen bonding between those molecules. In ethyl alcohol, we've got hydrogen bonding as well, but we don't have as many sites for hydrogen bonding, so it has less hydrogen bonding. And then diethyl ether is a polar molecule with weak dipole forces So you can see that the weaker the force, the lower the boiling point. And of course, the lower the boiling point, the easier it was for the attractive forces to separate, which means there would be a lower vapor pressure. Let's talk about soap. Soap is a unique molecule that has both a polar end and a nonpolar end, and because of this, it is an excellent cleaning agent. The polar portion can dissolve anything that is aqueous, meaning dissolved in water, and the nonpolar end can dissolve anything that is of dirt or grease, nonpolar molecules. The soap surrounds the dirt, and the outside of this unique structure called a micelle can interact with the water. The water does not see the nonpolar dirt. Soap can disturb water molecules' abilities to stick together, and it weakens the intermolecular forces, lowers the surface tension of the water molecule. This allows the water to spread out over the dirty dishes.